All right, welcome everyone. Today, we're going to tackle a topic that's, well, at the very heart of all programming, algorithms. And look, our goal here isn't to just throw a bunch of dry definitions at you. We want to really understand them, to grok them, you know? We're going to make these super powerful ideas feel simple, visual, and crystal clear.
So, have you ever run into this? You write some code, maybe a second version of it, and they both do the exact same thing, but one of them is just blazing fast, and the other one feels like it's crawling through mud. What's the deal? Well, that's where algorithms come in. The difference between a super snappy app and one that makes users want to throw their phone across the room, it's almost always the algorithm. So the big question is, how do we know which one to pick?
All right, so to figure out how to pick the fast algorithm, we need a way to measure speed, right? But here's the thing, we're not going to use a stopwatch. Instead, programmers use this really powerful idea called Big O notation. You can think of it as the language we use to talk about how efficient our code is. So what exactly is Big O? Well, it doesn't measure speed in seconds or milliseconds. That's because, my super fast gaming PC would run code way faster than a 10-year-old laptop, so that's not a fair comparison. Instead, Big O measures how the number of steps or operations grows as you give it more and more data. It's all about how the algorithm scales. Does it stay fast? Does it slow down a little? Or does it just completely fall apart when the input gets huge? Okay, and this table really brings it home. Just look at the difference when you go from 100 items to a million. For a linear algorithm, O of n, a million items means a million operations. Makes sense. But look at the logarithmic one, O of log n. It takes only about 20 operations. 20. And then you have O of n squared, which would take a trillion operations. A trillion! That's not just slow, that's completely unusable. This is the difference we're talking about between instant and totally broken.
And that's the bottom line, right? For the people using your software, picking an algorithm with a good Big O is everything. It's the difference between something that feels magical and instant and an app that just hangs and feels totally broken. If you want to build apps that can handle real-world data, you absolutely have to get this right.
Okay, theory is great, but let's make this real. We're going to look at our first major algorithm by tackling a super common problem you'll face all the time, just finding something in a list. And we're going to see just how big of a difference the right approach can make.
So let's start with the most obvious way to do this. We'll call it linear search. It's exactly what it sounds like. You start at the very first element and check every single one until you find what you're looking for. Yeah, it works, but its complexity is O of n. That means in the worst case, if you have a list with a million items, you might have to make a million guesses. We can definitely do better than that.
All right, now for the smart way, binary search. Now, there's one really important rule here. The list has to be sorted. Instead of starting at the beginning, we jump right to the middle. Our target is the number 7. We look at the middle, it's a 9. Okay, since our list is sorted and 9 is bigger than 7, we know our target has to be in the left half. Boom! In one single step, we just threw away half of the entire list.
So now we just repeat the process on this smaller list. We find the new middle, which is 5. Well, 5 is too low, so we know our target must be in the part to the right of 5. And just like that, we've cut our problem in half again.
And look at that. We're left with just one number, 7. We check it, and we found it. That's it. That's the incredible power of binary search, and O of log n right there. 3. That's it. It took us just 3 guesses to find our number in a list of 8. A linear search that could have taken up to 8 guesses. And yeah, I know 3 versus 8 doesn't sound like a huge deal, but remember that table? When this list grows to a million items, we're not talking about a million guesses anymore. We're talking about 20. 20 versus a million. That's not just an improvement, it's a total game changer.
And here's what that looks like in Python. It's surprisingly simple, right? You can see that while loop is our main engine. Inside it, we calculate the midpoint. Then, we have our if statements that check if the middle is our target. If not, we just move our left or right pointers, effectively throwing away the half we don't need. It's exactly the logic we just walked through, but now it's in code.
So, binary search is amazing, right? But remember that one big catch? The data has to be sorted for it to work. Which of course leads us to the next big question, what's the most efficient way to sort a list in the first place? So let's level up and dive into sorting algorithms.
Okay, so let's compare 2 different approaches. On one hand, you have something like selection sort. It's pretty simple to understand. You find the absolute smallest item in the list, move it to the front, and then you just repeat that process for the rest of the list. Simple, but because you're constantly rescanning the list, it ends up being O of n squared. And we know that's not what we want for big lists. Then, on the other hand, you have something much cleverer, quicksort. It's way faster, and it uses a really cool strategy to get there.
That clever strategy is called divide and conquer. And this is a big one. It's honestly one of the most powerful and important ideas in all of computer science. And the name basically tells you everything you need to know. You take a big, difficult problem, and you break it down into smaller, much easier to solve subproblems.
So here's how quicksort uses divide and conquer in 3 steps. First, you divide. You pick an element from the list, which we'll call the pivot. Second, you conquer. You rearrange the entire list so that everything smaller than the pivot is on one side and everything bigger is on the other. And third, you combine. And this is the magic part. You recursively do the exact same thing to those 2 smaller sublists, and you keep going until everything is perfectly sorted.
And check out the Python code for this. It's actually pretty elegant and short for such a powerful idea. The most important part to see is at the very end, where the quicksort function calls itself on the left and right lists. That's the recursion, the combine step, happening right there. And the lines before it? That's just us picking a pivot and partitioning the list, our divide and conquer steps. The code is a beautiful reflection of the strategy itself.
Wow, okay, we've covered a ton of ground, haven't we? We went from simply asking, why is my code slow, all the way to a powerful strategy like divide and conquer. So let's wrap this up and review the key tools you've just added to your programming toolkit.
So what are the big takeaways? First, remember that algorithms are just tools. Tools for solving problems in the smartest, most efficient way. To measure that efficiency, we have big O notation, which tells us how well our code scales. We saw the incredible power of O of log n with binary search, which is just a fantastic way to search. For more complex problems, we learned about divide and conquer, the master strategy behind quicksort. And at the end of the day, all of this is absolutely crucial, because these efficient algorithms are what let us build fast, scalable apps that users love.
You know, at the end of the day, learning this stuff isn't just about passing a coding interview or making some code run a little faster. It's about learning a whole new way of thinking. It's about finding those clean, elegant solutions to really tough challenges. Honestly, it's kind of like getting a superpower. So now you've got it. The only question is, what problem are you going to solve with yours?